How do you model the value of an investment that earns compound interest? There are three formulas we use. Let's see, value sub t equals the principal times 1 plus the interest rate and t the years. If we're going to do it annually, if we're going to do it more than annually, that would be v sub t equals the principal times 1 plus the rate divided by the number of times a year to the nt power. And that's if we're going to do it more than annually, but not continuously. Continuously, that would be v sub t equals p, and then we use the number e to the rt power. All right, so that's the three ways. Comparing simple and compound interest. A bond is a type of investment that you buy with cash and for which you receive interest either as the bond matures or when it matures. A conventional bond generates an interest payment, sometimes called a coupon payment, on a regular basis, typically twice a year. The interest payments end when the bond matures and the amount you paid up front is returned to you. A zero coupon bond, on the other hand, requires you to invest less money up front and pays you its maturity value, which includes all accumulated interest when the bond matures. Over the life of the bond, the interest that is earned each period itself earns interest until the bond matures. The basic difference between a conventional bond and the zero coupon bond is the type of interest earned. A conventional bond pays simple interest, where a zero coupon bond pays compound interest, which is interest that earns interest. For $1,000, you can buy a conventional bond that has a maturity value of $1,000, has a maturity date of 4 years, and pays 5% annual interest. Calculate the interest that the investment earns annually by completing the table. Bear in mind that the interest earned is paid to you and not reinvested. Okay, so we have year one, $1,000, and then 1,000 times 0.05 is $50. Value of the investment at the end of the year is $1,000 because they paid it to you. They don't put it on the bond. Again, $50. Again, $1,000. Again, the interest earned is $50, and then $1,000. Again, the interest is $50, and again, it is $1,000. And then they give you back your interest, or your bond, or they give you back your money, your $1,000. That's a conventional bond. For $822.70, you can buy a zero coupon bond that has a maturity value of $1,000, has a maturity date of 4 years, and pays 5% annual interest. Calculate the interest that the investment earns annually by completing the table. Bear in mind that interest earned is reinvested and not paid to you until the bond matures. In other words, each year you're not going to get a check for $50. Okay, so this is a zero coupon bond. $822.70 is what you paid them. They multiply that by 0.05, and you got $41.14. Well, they add that onto that $822, and you got $41.14. So now at the end of the year, it is worth $863.84. All right, beginning the next year, $863.84. They take that $863.84, multiply it by 0.05, and the interest that you earn that year is $43.19. So they're going to take that $863.84. They're going to add $43.19 to it, and your bond is now worth $907.03. $907.03 is what it is at the beginning of year 3. They take the $907.03, multiply it by 0.05, and you get $45.35. All right. Now they're going to take the $907.03. They're going to add $45.35 to it, and your bond is now worth $952.38. So at the beginning of the 4th year, it's worth $952.38. $952.38. Multiply it by 0.05, that's $47.62. Bounce that up there. $952.38 plus $47.62. It is now worth $1,000. Okay. So basically, you give them $822.70, and then 4 years later, they give you $1,000. That's interest. Describe the difference between how simple interest is calculated and how compound interest is calculated. Well, simple interest is calculated from the initial amount only. Simple interest is calculated from the initial amount. That's terrible penmanship. Only. All right. And then compound interest is calculated from the initial amount and the interest accrued. And the interest accrued at that point. All right, good. If V sub t represents the value of an investment at time t and whole numbers of years starting with t equals 0 and ending with t equals 4, write a constant function for the last column in the first table and an exponential function for the last column in the second table. So for the first table, that would be V sub t equals 1,000. All right. And then for the second, that would be V sub t equals $822.70 times 1.05 to the t power. All right. Modeling interest compounded annually. Recall that the general exponential growth function f of x equals f of t equals a times 1 plus r to the t power. When this function is applied on an investment where interest is compounded annually at a rate r, the function is written v sub t equals p times 1 plus r to the t power, where v sub t is the value of the investment at time t and p is the principal amount invested. Go ahead and read through A, and when you get back, we'll do B together. All right, glad you're back. A person invests $200 in an account that earns 6.25% interest. Find the value of the investment when it reaches $5,000. So we're going to let P equal $200. And R is going to equal, this is 6.25%. So that's going to be 0.0625. Then B sub T equals, and then we got the principal, which is $200, and then 1 plus R. So 1 plus 0.065 will be 1.0625. And then we're going to graph the function on the graphing calculator. And we want to know when it's going to reach $5,000. So we're going to also graph 5,000. Okay? So let's see here. All right, I went ahead and put it in the calculator. So that's 200 times 1.06, and it's 25. It doesn't show it. Now we're also going to graph the 5,000. So tab 5,000 and press enter. Now, if you look, see, I got 10,000 up here, and I got like 100 over here. And menu 4.1, and that'll show you my settings. Okay, and I went ahead and did that because when you first graph it, you're not going to be able to see it. Okay, but I'll show you a couple tricks to figure out where to be. Menu 6, 4, and then look, it's going to take 53.1 years. Okay, 53.1 years. So let's all right. So the value of the function is $5,000 at approximately 53.1. So the investment reaches a value of $5,000 in approximately 53.1 years. Now, how in the world can I tell how to set my calculator up? Well, you want to know when it reaches $5,000, right? So your y-axis has got to be greater than $5,000. Okay, and as far as your x, you kind of got to figure. You kind of got to guess a little bit, and you may not get it right. You might have to do it a time or two. Okay, your turn. A person invests $1,000 in an account that earns 5.5% in annual interest. Find when the value of the investment has doubled. So want to know when it's doubled. So they're going to want to know when it equals $2,000. All right. So my principal is $1,000. All right. And my interest rate R is 0.055. So let's put that in, and we got B sub T equals 1,000. That's the principal. And then 1 plus 0.055, and then that's going to be in T years. So B sub T equals 1,000 times 1.055 to the T. And then we're going to also want to graph 2,000. So let's go over here, and I went ahead and graphed it. See, I got, maybe I didn't graph that one. Is that one not in there? I guess I didn't. So let's see here. And then we'll control doc, and we'll put us a new page in there. All right. So what do we got? We got 1,000. 1, 2, 3. Open parentheses. 1.055. Close parentheses. Caret X, because we don't have a T. All right. And watch, when you press enter, you can't see it. Okay. Well, what do we know? We know 1,000 is A, so that's going to be where it crosses the x-axis. So we'll menu 4, 1, and X min, I'm going to put -1. And then, so it shows the bar at the bottom. And I know it's going to cross the x-axis at 1,000, and I'm wanting to know when it crosses 2,000. So I'm going to put 2,500 here. And I'm going to use, I'm still on the x's. That should be really for the, let's see here. That should be for the y. Control, delete. So that's -1. And that is going to be, I'm going to put 2,500 and a tab of 500. Now the X, I'm just going to have to guess how long that's going to take. And so that -1. And to be on the safe side, I'm going to go big. 20 years. I'm going to say 20 years. And I'm going to use a scale of 5. Okay. Because remember, the T is the X scale. All right, so not too bad, not too shabby. And we want to know when it hits 2,000, so I'm going to graph another line at 2,000. 2, 1, 2, 3. That's going to be towards the top of the screen. All right, good. And then find out where they cross. 6, 4, menu 6, 4. And that gives me 12.9 years. So that's going to be 12.9 years. So T is approximately 12.9 years. 12.9 years. Let's see here. Modeling interest compounded more than once a year. Interest may be earned more frequently than once a year, such as semi-annual, every 6 months, quarterly, every 3 months, monthly, 12 times a year, or even daily, 365 days a year. If the number of times that interest is compounded in a year is n, then the interest rate per compounding period is r divided by n, where r is the annual interest rate, and the number of times the interest is compounded in t years is n times t. So the exponential growth function becomes v sub t equals principal p times 1 plus r over n to the nt power. Go ahead and read A, and when you get back, we'll do B together. So B, a person invests $600 in an account that earns 6.25% interest rate, annual interest rate, compounded semi-annually. Find when the value of the find when the value of the investment reaches $1,700. So the principal is $600. The rate is 0.0625, and n is semi-annually, so that's going to be twice, right? Twice. So let's fill that out. We've got $600, and we've got 0.0625 divided by 2, and that's going to be 2t. So that's going to be $600, and then 0.0625 divided by 2 is going to be, well, it'd be 1.03125 and 2t. So we'll put this in the calculator. We'll put that in the calculator. And really, if you want, you can put it in there like that. It'll do it for you. So let's see here. Graph the function on the graphing calculator. Also graph the line y equals 1,700. 1,700. All right. So let's see here. There it is. 600, 1 point. And now we need to press tab in 1,700. And where do they cross? Menu 6, 4. And there it is right there. So it's going to take about 16.9 years. And notice 5, 10, 15, 20, 25, and then 2,500. plenty of room on both sides. So 16.9 years. So the value of the function is $1,700 at approximately 16.9 years. 16.9 years. Not too shabby. Not too shabby. Your turn. A person invests $8,000 in an account that earns 6.5% annual interest compounded daily. Find the value of the investment when it reaches $20,000. So your Y scale is going to have to be kind of tall because you got 20,000 right there, right? So the principal is $8,000. Your rate is 0.065, and it's compounded daily. Well, there's 365 days in a year, so N equals 365. So V sub t equals the value at time t would be 8,000, and it's 1 plus 0.065 over 365, and that's going to be 365 to the t. All right, if you simplify it a little bit, that would give you 1.000178, and that's 365 t. All right, so let's go ahead and graph that. See, now notice I didn't simplify it. I just put it in there just the way it is, right? Okay, and I got my Y scale up to 25,000, and I hope I got this out far enough. So we're going to press tab and put in 20,000 because that's what it's wanting to know. 20,000. Enter. There it is. Good. So let's find that spot. Menu 6, 4. So it's going to take 14 years, 14.1 years. So T is approximately 14.1 years. Modeling interest compounded continuously. Now it's a party. By letting M equal N divided by R, you can rewrite the model V sub t equals P times 1 plus R over N to the NT power as V sub t equals P times 1 plus 1 over M to the MRT, because R divided by N equals 1 over M and NT equals MRT. Then rewriting V sub t equals P times 1 plus 1 over M to the MRT as V sub t equals P times, and then that would be 1 plus 1 over M to the M power to the NT or RT power, and letting N increase without bound, which causes M to increase without bound. You see that 1 plus 1 over M to the M power approaches E, and the model simply becomes V sub t equals P E to the RT power. This model gives the value of an investment with principal P and annual interest rate R, when interest is compounded continuously. All right, so go ahead and read through A and follow along, and then when you get back, we'll do B together. All right. The principal amount, $350, earns 6% annual interest compounded continuously. Find when the value reaches $1,800. So our interest rate is $350. Our principal is $350. Our rate is 0.06. Then V sub t equals 350 E to the 0.06 t. Graph the function on a graphing calculator Also graph the line y equals, y equals 1,800. That's what we're wanting to know is when it reaches 1,800. So what would be $1,800, 1800, and find the point where the graph intersects. So let's go graph that. Let's go graphing. There it is. I already got it in there. So we're wanting to put, press tab, and we're wanting $1,800. We're wanting to know when it reaches $1,800. Way up here. All right. Menu 6, 4, and that's going to take 27.3 years. 27.3 years. So the value of the function is $1,800 at approximately 27.3. So the investment reaches a value of $1,800 in approximately 27.3 years. Think about it. You put in $350 and it's now worth $1,800. That's a lot. That's a lot. Your turn. A person invests $1,550 in an account that earns 4% annual interest compounded continuously. Find when the value of the investment reaches $2,000. So what do we got? We got the principal equals $1,550. The rate is 0.04. So the value of the investment will be $1,550, and it's compounded continuously, so that's going to be E. Our rate is 0.04 to the T. We want to know when it reaches $2,000. So let's go to our graph. I don't have another one then. No. Oh, control doc. Let's put one in. So it was 1550, 1550, and then the number E to the 0.04, and you got to use X power, and we'll hit graph. Can't see it. All right, so we know it's going to cross the X-axis at 1550, and we know we're looking for $2,000 on the Y-axis, and so and I'm not sure how long that'll take on the X-axis. So for 1, I'm going to put -1, and then I'm on 20 years, and then I'm going to say 5 there, so it's not too. And then my -1, and then I know I'm looking for it to pass 2,000, so I'm going to just go ahead and put 2,200, and let's see, 500. All right, let's see what. So that's up there like that. What if I do it like this? Okay, I can grab it down a little bit. All right, and I need to know 2,000, right? So press tab, and I'll put 2,000. Press enter. There it is. There it is. So menu 6, 4, and it says 5. Let's see. Now, how did I get 0.04? Press tab. It should have been 0.04. I don't know how I got a 3 there. I'm glad I caught that. So I got 6.37 years. All right. So what do we got? I got T is approximately, and it was 6.37 years. 6.37 years. Cool. Now, finding and comparing effective annual interest rates. Okay, the value of an investment function V sub t equals P times 1 plus r over n to the nt power equals P times 1 plus r over n to the n t power, where interest is compounded n times per year, is an exponential function of the form f of x equals ab to the t power, where equals p, the principal, and b equals the growth factor, 1 plus r over n to the n power. When the base of an exponential function is greater than 1, the function is an exponential growth function where the base has where the base is the growth factor and 1 less than the base is the growth rate. So when the growth rate for b sub t equals p times 1 plus r over n to the nt power is b minus 1 equals 1 plus r over n to the n power minus 1. This growth rate is called the investment's effective annual interest rate, R, where R is called the investment's nominal annual interest rate. Similarly, the value of an investment function v sub t equals p to the p times e to the rt power, p times e to the r to the t power, where interest is compounded continuously. The growth factor is e to the r, and the growth rate is e to the r minus 1. So in this case, the effective annual interest rate is the rate that would produce the same amount of interest if interest were compounded annually instead. The effective rate allows you to compare two accounts that have different nominal rates and different compounding rates. All right, A, just go ahead and read A and follow it through. When you get back, we'll do B together. Harriet plans to make a deposit in one of two accounts. Account A has a 3.24% nominal interest rate with interest compounded continuously. And account B has a 3.25% nominal rate with interest compounded semi-annually. Now, see, you're not comparing A's and B's. It looks like B is better, doesn't it? Because it's 3.25, where the other was 3.24. But if you notice, A is compounded continuously, but B is compounded semi-annually. To maximize the interest that the account earns, which account should she choose? Okay. For account A, interest is compounded continuously. The nominal rate is 3.24%, so that's going to be 0.0324. So RA equals e to the R, well, it's going to be 0.0324 minus 1, which is approximately 0.03293. Okay, when we simplify. All right. For account B, interest is compounded semi-annually. So N equals 2. The nominal rate is 3.25%, so R equals 0.0325. All right, so let's put all this in. 1 plus R, that's going to be 0.0325 divided by 2, and then that's going to be 2 right there. All right, put all that in your calculator, you get 0.03276. So account A has an effective rate of 3.29%, and account B has an effective rate of 3.27%. I rounded a little bit. So account A has the greater effective rate, and Harriet should choose account A. All right. See how they can be kind of deceptive. So you got to kind of. Jacqueline plans to make a deposit in one of the accounts shown in the table. To maximize the interest that the account earns, which account should you choose? All right, so account X has a nominal interest rate of 4.24%. Account Y has a 4.18%. Account X is annually, once a year, and this is daily. Okay, so account X, and we'll put over here account Y. All right, so N equals 1, because that's annually. Daily, N equals 365. All right, R is 0.0424. R over here is 0.0418. Okay, so the effective rate will be 1 plus 0.0424 over 1 minus 1, which, put in your calculator, is 0.0424. All right, let's go over here. The effective rate of Y is 1 plus 0.0418 divided by 365 minus 1, and put that all in your calculator. You get 0.04268. Okay, I think I would choose Y. It's a little bit more. It's a little bit more. And over the long haul, that's going to be more money in your pocket. Explain the difference between an investment's nominal annual interest rate, and its effective annual interest rate. Well, let's see. Since we saw, interest rates can be calculated several ways. Okay, several ways. They can be done annually. They can be done semi-annually, quarterly, continuously, 365 days a year, monthly. It's hard to tell which one is actually earning you more interest. Now, see, the bank, they don't want to pay you no more than they have to for your money, but you want to make as much money as you can off of it. So the nominal interest rate, uh, the nominal interest rate uses, the nominal interest rate here uses V sub t equals the principal times 1 plus r over n to the nt. All right. And then the effective annual rate uses, the effective annual interest rate uses p to the 1 plus r to the t power. So basically, if you turn them into this right here, then you can compare which one will actually earn you more interest, more money each year. So that's kind of what you need to do. Let's see here. Maybe this will send you quick. List the three functions used to model. So you got v sub t equals p times 1 plus r to the t. Now that's if it's compounded annually. All right. Now, if it's compounded any other way than annually or continuously, you want to use 1 plus r over n to the nt power. And we'll just say it's more than once a year. And if it's going to be continuously, you're going to want to use p to the e to the rt, and that's for continuously. All right. So, and there you have it. Good lesson, folks. See you tomorrow in class, and have a good evening.